I have to apologize that it's not really directly related to electroweak phase transition, because I will try to make some link, but in practice, if there are cosmic topological defects, they wouldn't be electroweak ones. So this is not. This is perhaps more interesting at the sort of general level, because the physics of how topological defects form in phase transitions is in many ways similar to electroweak baryogenesis. So and it's also easier to understand and easier to calculate things. So this is sort of a toy calculation, simpler version of electroweak baryogenesis in many ways. Right, so a topological defect is basically an object in field theory which is localized and topologically stable, and they exist generally in systems with spontaneously broken symmetries when the vacuum manifold, so the set of different possible vacua is topologically non-trivial. Because then what can happen is, so you have some different possible vacua which are related by the symmetry, and if in different directions the system approaches a different vacuum, then you often, and if the vacuum manifold has non-trivial topology, then you can get in a situation where there's a frustration that somewhere in the middle, but the system can't be in the vacuum. And the simplest example is a domain wall. So here's just a picture of a domain wall network. So there are two different vacua, there's red and there's blue, and between them you have a domain wall. So depending on the topology, if the zero homotopy group is non-trivial, then you have domain walls. If the first homotopy group is non-trivial, so the vacuum manifold is not simply connected, then you have strings or vortices. If the second homotopy group is non-trivial, you have monopoles, and if the third homotopy group is non-trivial, you have textures. Now for cosmology, yes.
Can one simply define these pies?
So this is the homotopy group, and what it means is it classifies. You have the vacuum manifold is the yeah. So the simplest example, the example that I will focus on is are strings. So you have a potential with U1 symmetry like this, and there's a circle of possible vacua. So the vacuum manifold is in general the set of different vacuum states, and now if you think of the field values, the values of the order parameter at infinity, in let's say a three-dimensional space, think of different situations. First of all, let's look at the whole surface of this box at infinity. That's the topology of a sphere, so it's an S2. And the field values on the surface are therefore a map from S2 to the vacuum manifold. If you assume that the field is in the vacuum, the system is in vacuum at infinity, and what the homotopy tells you is whether you have different classes of such map that cannot be continuously transformed to each other. So if you have a field configuration that has a non-trivial topology, it corresponds to a non-trivial element of the homotopy group, it means that you can't continuously transform it to a trivial map, so to a vacuum solution. So the homotopy group is just a mathematical way of classifying, so pi 2, so this is what, so pi 2 corresponds to maps from S2 to M. So pi 2 tells you whether the field values at the surface at infinity can be continuously transformed into a trivial vacuum. If they can't, then it's the same is true for the field configuration. You can't continuously change the field configuration so that it goes into vacuum state. Therefore, you have there's a topological reason why your configuration can't decay. Now, then you can also look at just a curve here at infinity, and that is a topology of S1. The map here gives you a map from the field values here gives you a map from S1 to M, and those are classified by the first homotopy group. And so this is really just an abstraction.
So that's why higher pi's don't play a role.
That's right. So
because
in
we have 4
3 dimensions, really the only ones that are sort of proper topological defects are these. And then the texture is a sort of a boundary case, which is a borderline case, which is not strictly speaking a topological defect, but there is still some topology going on.
But the main case would now be you have, let's say, a discrete set of vacua which would lead to walls.
Yeah, that's right. So that's pi 0 when you're just looking at points here and or the different ends of your box, so that they are in different. So if they are in different vacuums. So if you have a discontinuous, if the vacuum manifold consists of disconnected pieces, then the zeroth homotopy group is non-trivial.
And the dimension goes. I remember this. That the dimension goes down to 1 and 0, and then pi 3 is even.
So S0 is well, yeah. So yeah, S0 is just a set of 2 points. Plus 1 and minus 1. And so basically, I mean, you don't need to know that these are called homotopy groups. That's not terribly important, but it's just that if you have figured out what the vacuum manifold is, then you can go and look at tables. If it's something complicated, but it's not obvious what kind of configurations you can transform to each other. People have studied the homotopy groups a lot, so these are listed in tables, and therefore it's just a sort of systematic and nice way of classifying the difference. Right, so anyway, what I will be mostly talking about are vortices. So that corresponds to this case where you look at a circle at infinity, and the field values there go around the circle on the vacuum manifold, so therefore you can't continuously turn that into a vacuum solution. So it basically is a solution that looks something like this. The different colors here correspond to different phase angles of the order parameters. So some scalar field, there's U1 symmetry, so there's a rotation symmetry around the axis here, and here I try to sort of visualize the fact that in different directions around the string, the field approaches a different vacuum state corresponding to a different color, and that's a vortex, or in a 3 dimension, it's a sort of line-like, string-like solution, so it's called string. Well, written it here as Nielsen-Olesen string, but it isn't actually. A Nielsen-Olesen string it is one in case. So this is just a global U1 that I have here. So anyway, this is a vortex, and obviously if the field approaches these values at infinity, it can't. That makes the string stable. It can't just decay without having to change the field values at infinity. Okay, so in cosmology, these strings, if they exist, this kind of object, they're called cosmic strings. So they would be stable, topologically stable, typically very massive, line-like objects. But because they don't have, so in a gauge theory, vortex solutions don't have any long-range forces, and therefore the only interaction they have in practice is gravitational interaction, and therefore the only parameter you really need to know about the string is its tension, which is energy per unit length, because it's how heavy it is. And from grand unified theories, you could produce these from grand unified theories, and then the tension mu in units of the Newton's constant of Planck mass is 10 to minus 6, roughly.
Is it clear why a string cannot be charged? Let's say I have an electric charge in a sufficiently complicated model?
Yes, I mean, yeah, it could. You could certainly write down a model in which it would be more complicated. So people normally just look at the simple case. Also, obviously, if you have an electric charge, if a string has an electric charge, then the dynamics becomes more complicated because they have long-range interactions.
So maybe more interesting.
You could say that it's more interesting. Much less is known about that.
But it's not excluded right away.
Yeah, I don't think it is excluded. I mean, certainly people have studied strings on which there is some other charge, but normally a global charge, traveling around the string and stabilizing it against collapse. So I would imagine that there's nothing really wrong with having an electric charge, but I'm just sticking to the simplest case. Now, yeah, just to mention that a reason to people have got more interested in cosmic superstrings, which are just string theory strings stretched to cosmological scales, but they would look very similar. But in that case, you have more flexibility for the tension, so the tension would generally be within that range. Now, obviously, people have tried to look for these, and there are different ways. I won't go into any detail here, but different ways of searching for them in the cosmic microwave background. You can look at first the temperature perturbations that they would generate when they move around, and that's, I mean, all their effects are given by this parameter G mu, and essentially the amplitude of perturbations that you would get is given by G mu, and because we know we have measured the amplitude of perturbations to be roughly 10 to minus 5, and the spectrum isn't what strings would predict. It means that there's an upper bound of roughly 10 to minus 6, because the contribution, if there are strings, their contribution has to be below the contribution from inflation. In future, when Planck and other experiments can measure the polarization of the light better, there's hope to improve this bound a little bit. There's a similar bound coming from gravitational waves. So the strings, when they evolve, they emit gravitational waves, and when gravitational wave goes between us and the pulsar, it would affect the frequency of the pulsar that we observe, and therefore by measuring how stable the frequency is, we can put an upper bound here. Get an upper bound on the amplitude of the gravitational waves, and that's again proportional to the tension. That's similar to what you get from cosmic microwave background.
What's the typical frequency of these gravitational waves?
So, I mean, I don't know. Yeah, I have to say I don't know.
And what would be the typical frequency of these gravitational waves?
Yeah, so I don't. Yeah, I have to say I don't really know. Now there's hope that with future gravitational wave experiments we can do, people can do better than these. So if LISA ever flies, then at least in principle, it would be able to push the upper bound to roughly 10 to -10, and then it would really rule out or observe GUT, grand unified theory strings. Okay, and so cosmic strings are just hypothetical objects. They haven't been observed. They very well may not be. They don't have to exist. However, there are other kinds of topological defects which definitely do exist, and people can study them in the lab. There are vortices in liquid crystals where the order parameter is the orientation of the liquid crystal molecules. It's a rod-like molecule, and you can see them using polarized light. There's a picture. The vortices are the crosses there. In superfluids, the order parameter is the atom wave function, and here these lines are vortices. You can take pictures of them. Bosons and condensates, again, atom wave function. The dots here are vortices, and in superconductors it's the Cooper pair wave function, it's the order parameter. And again, people can study this. So this whole thing is in a sense very universal. The basic principles that because at the theoretical level all of these are similar objects, so the basic principles of how they form should apply both to cosmic strings and to these experimental situations. Okay, so what I was mostly going to talk about is how these objects form when you have a phase transition. And it's easiest to understand it, the mechanism, the picture is simplest in first order transitions where you have bubbles of the broken phase nucleated. And so when nucleate the bubble of broken phase, the field has to choose some direction. You have this vacuum manifold, and all of the points in the vacuum manifold are just as good vacuum states, but each bubble has to be in one vacuum. So you can have bubbles, as in here, and different colors corresponding to different vacuum states. And the bubbles then grow, and eventually they collide with each other, merge, and the whole system eventually goes into the broken phase. However, because the bubbles can have made different choices of which vacuum to go to, for instance, if you get the collision of three bubbles like this in the U1 theory, there is a probability of order 1 that when you interpolate between this bubble to this bubble to this, and this bubble to that, the phase angle changes by 2 pi, so you get the vortex there between the bubbles, the place where the bubbles meet. And because the probability of that is just some number, and so therefore if the size of the bubble, radius of the bubble is r, you get an order of magnitude estimate that the number density of these strings per cross-sectional area have to go like 1 over bubble area of 1 over r squared.
Do these strings then end somewhere?
The strings don't end, so obviously you're going to have more bubbles. There's another bubble somewhere here.
It's very non-local thing.
Well, I mean, the physics is all local, but yeah, I mean, if you just think of it, if you had a fourth bubble somewhere here on top, you already know that these bubbles are in what they are. If you add one more bubble, you can see that the string will never end. Just the fact that these have already these phases. If you add one more, the string will always continue somewhere, and it is because of the topology of the vacuum manifold. The strings can't end. So the formation process is completely local, but the strings are extended non-local objects. It can be either loops or infinitely long. Okay, the strings also, defects also form in second order phase transitions where you have a gradual change from the symmetric to the broken phase. It could be because of decreasing temperature, or in cosmology, and the end of inflation, or some other change in the system, in an experiment changing the pressure. And so basically then the potential changes gradually, but the same thing happens. The field has to choose a direction which way to go, and it can't choose the same direction everywhere because there's a finite correlation length psi, and in cosmology it has to be shorter than the horizon line, just by causality. And so therefore you still have a Kibble mechanism here. Instead of bubbles, you have now domains which are less well defined, but still you have some kind of domains in which the field is more or less uniform, but between which it's uncorrelated.
Determines the correlation length in such a second order phase transition?
Sorry?
What determines the correlation length in such a second?
Yes. So so the correlation length, of course, in principle, if the phase transition was adiabatic, the correlation length would diverge at the second order phase transition point. However, in practice, in any experiment, you want the phase transition to complete in a finite time, and therefore the correlation length can't diverge because of cosine. It can't grow faster than the speed of light. So there's some upper bound on how big the correlation length can be. And in fact, one can estimate what value the correlation length freezes out to by looking at the critical dynamics in terms of the critical exponents. Basically, you start from high temperatures, you cool down the system. In principle, in equilibrium, in an adiabatic change, the correlation length will diverge, but at some point the field will fall out of equilibrium. It can't adjust to the change, and it will freeze out to some value psi hat, which one can easily figure out that it should go with the cooling rate tau q to some power which is given by the critical exponents of the universality class. So this is a nice prediction which has been.
T is a physical time, yes? Big T.
It's temperature.
Oh,
Yes. So yeah, tau q here is the sort of time scale. It measures how fast you are cooling. T here is just it's the temperature.
And what is the value of the new?
Sorry.
What is the value of?
Yes, and it depends on the universality class of the transition. So for different theories, you have different critical exponents, which are normally between 0 and 1. So 1/2, 1/6.
Do you know the values of phi to the 4th theory?
Sorry.
Do you know the values of phi to the 4th theory?
Phi to the 4th. Yes, so in 3 dimensions, it's a U1 theory. It's not known exactly, but it has been calculated numerically. And I think it's 0.67 and some more numbers. But
it's 2/3.
Roughly, but it's not exactly 2/3.
And tau q is basically, well, if you're in the early universe, it's basically Hubble time, I suppose.
Yeah, exactly. Yes. Yeah, I mean, roughly. I mean,
Yeah.
at the level of order of magnitude. Yeah. Okay, and so this prediction, I mean, this is a definite prediction which one can go and test, and it has been tested in simulations and also in experiments with the systems that I showed, and it seems to work nicely. So here is just a simple movie of how this works. So we start in the symmetric phase, different colors here are again different phase angles, cool the system, and get these domains of different colors and the dots between them, the black dots are vortices. Okay. So that was known as the Kibble mechanism, and that is a very good description of defect formation when we are talking about global symmetries. However, what we are usually more interested in are gauge symmetries. So we want to add a gauge field to the system. Partly because if you have a global U1, the strings that you get would not be the kind of strings that we like in cosmology, because they would have long-range forces. Simply because there's a spontaneously broken global continuous symmetry, you have a Goldstone particle which gives long-range interactions for the strings, and it's not really, it's harder to study them. We don't really know how they would behave in the early universe.
So you mentioned this the other day, but since it's not known how they would behave, there's no reason to rule this out.
Yeah, there's no reason to rule it out, and it may even be more, I mean, it may even be desirable from the observational point of view. It would possibly they might even be better from the observational point of view, but it's just that it isn't known how they behave. And so that's the main reason why people like to focus on local strings. Also, yeah, I mean, for instance, if you want to think of these strings as coming from superstring theory, then most of the time they would be correspond. They would be more like gauge strings because they carry gauge flux. So yes, there's no reason to really exclude the global strings, but people just like to study gauge strings. And so that's what I'm also going to do. And if you think of these condensed matter laboratory systems, liquid crystals, Bose-Einstein condensates, and superfluids have global U1 symmetry. Superconductors have a local one because Cooper powder is electrically charged. So this corresponds to superconductors, whereas the previous case corresponds to essentially any other laboratory.
So you said that the cosmic strings for a global U1 haven't been studied, but since you have laboratory examples in condensed matter systems of strings associated with Goldstone loads, what's the impact observationally there?
Well, I don't think people have studied the kind of questions we would like to know about in cosmology. I mean, I think
just
that's
the patterns of vortices and superconductors versus other systems that don't have a local U1.
I mean, certainly there are. One can see. I mean, because they have the long-range forces in superconductors, the vortices when they form, they get basically stuck where they are. Whereas in liquid crystals, they move around and annihilate much faster. So one can do these things, and it is true that one could try to design an experiment to really study cosmological aspects, and there have been some attempts of that, but nothing really concrete is known. But I mean, I think it is something that is an interesting thing to do, certainly. So if we add a gauge field, the energy density for a static configuration would look like this. So you have the magnetic field, you know, that's just a B squared, so the magnetic field, and the gradient term gets replaced by covariant derivative, which involves the gauge field. And so now the symmetry is not just rotations of the phase, but you can rotate it by different amount at different points if you compensate for that by changing the gauge field. And what that means is that, strictly speaking, you can't break the symmetry. You can always rotate the phase to whatever you want. But there still is a phase transition. It's just that it's really strict, rigorously speaking, it's no longer a symmetry breaking phase transition. So it's very much like in the Electroweak theory. However, because the phase angle can be rotated at will, it's no longer physical observable, so then you have to really ask whether the Kibble argument, which was based on different phase angles in different bubbles or different domains, whether that is still valid. And what I will argue is that it isn't at least the whole story. And to understand what happens, let's see what happens when you go into the Higgs phase, or broken phase in this case. So what you want to do, essentially, what the system tries to do essentially is minimize the energy, let's say inside a bubble, inside a domain. And in the global theory, that just meant that it tries to minimize the gradient energy, and therefore the field became uniform. The complex phase in the whole bubble was uniform. But now, if you have now what you want to minimize is this, and essentially instead of the gradient, you want to minimize the covariant derivative. And to do that, you just have to have A, E, coupling E times the gauge field equal to the gradient. And you can do that either by changing the gradient, making the phase uniform, or by changing the gauge field. So you can cancel the gradient energy by changing the gauge field. And that changes the dynamics quite significantly. So here I try to make more specific connection with Electroweak theory. This is something that Anders, I think, has already talked about, and maybe we'll talk more about on Friday. But so in the Electroweak theory, as I said earlier, there aren't really any topological defects, but the vacuum manifold is topologically non-trivial, and the third homotopic group is non-trivial, which means that there are textures. Now, texture is not really a topological defect because it's not localized, but it means that in a sense there is some winding number in the whole space. So it's a map where you're not looking at the boundary. I mean, these were all boundaries going to map vacuum manifold. You look at the whole space, which you can, if you compactify that infinity, you can think of it as a 3-sphere. And the system, the field can be in the vacuum in the whole space at the same time. So there is no localized point at which you have energy concentration, but it can still have a non-zero winding number, and if it has, then there's gradient energy, and you have a texture. And these textures can form by the Kibble mechanism.
So can one characterize the vacuum manifold more precisely?
The vacuum manifold is so you should just have complex.
It's S3 again.
Well, so yeah, you have. So it's a complex doublet. So you have four.
Yeah, it's three-dimensional manifold. This is kind of clear.
Yeah, that's right. And I mean, I think it has a topology, in fact, of a 3-sphere.
Yes, it's S3. You
Yeah.
can think
What
of,
is the topology of a 3-sphere? Is
you
it?
can think of, if you have it in 1 dimensions, you have U1 in the circle, and then you can just take a ribbon and wind it. That's like a texture in 1 dimension.
Yeah.
Sorry, can you say it
Or
again?
if you take a ribbon, a strip of
Yeah.
paper and
Yeah.
wind it, that's like a texture in 1 dimension.
Mhm.
So this is obviously more abstract, but it is roughly the same. So basically, in one dimension.
But you say a 3-sphere has like a 1-sphere is a non-trivial topology. A 2-sphere, I guess, we would say it has a trivial topology. A 2-sphere.
No, I'm not saying that.
We would say that. But it's a, okay.
It's just characteristic of the
Not really topology.
topology of the boundary of the space is the same as the vacuum manifold. Then I think you have this pi3 is set, and then you have texture.
Yeah. So basically, a texture. If you had a one-dimensional system with U1, you would have texture. So here, this is a sort of circle, the vacuum manifold, this is X. And at different points, the vacuum would obviously be just constant. The texture would correspond to a configuration where you wind around so smoothly.
Also, you say we
wind
can
around.
take these two S3s and kind of, as you said with the ribbon, we
Yeah.
can try. Okay.
Yeah. And so you can have these, or you could have textures if it was a global SU2, but it isn't, and you have a gauge field. And again, the gauge field can compensate for this gradient energy. So the only energy that a texture has is because it is on the vacuum manifold at every point. The only energy it has is the gradient energy. The gauge field can compensate for that, and so it can basically remove the whole texture. But when it does that, the topology of the gauge field changes. So the vacuum, the zero energy state corresponds to, so the texture has some winding number, and when you compensate for that by the gauge field gets a Chern-Simons number which is equal to...
So in other words, the energy minimization locks Chern-Simons number to this texture winding number.
Yes, exactly. You minimize energy and that locks, but the two have to be equal. The Chern-Simons number of the gauge field has to be equal to the winding number. Now this can happen in two ways. If you think of first forming a texture and then let the system evolve, it tries to achieve this. And it can either do it by changing the Chern-Simons number to be equal to the winding number, or it can change the winding number to be equal to the Chern-Simons number. And it turns out that this depends on how big your texture is. And so you can have either of those happening. And what is interesting is that...
Let's see, just back, so I lost one line of your logic.
Yeah.
So you started with a U1,
Yes,
but you don't have this anomalous, you don't have any anomalies in the U1 theory, right, in this anomaly.
but this is not the Electroweak Theory, this is SU2.
This is an SU2.
Yeah.
Okay, sorry.
Yeah. Yes. So I'm just trying to see, to give an example of the same thing happening in a more realistic theory.
I see, okay.
And so you can either change this or that. And interestingly, if you have CP violation, it biases this process. So if you have a positive winding, so go that way, the threshold, the critical size at which you go between Chern-Simons number and winding number is different from a negative winding. And so if you have CP violation, it means that you, even though you formed the same number of, on average you form the same number of positive and negative winding textures. With CP violation, you end up with a non-zero Chern-Simons number on average, because the positive ones are less likely to unwind, more likely to be compensated by the gauge field than the negative ones. And so this gives you a non-zero Chern-Simons number, but there is an anomaly, obviously, in the Electroweak Theory, the standard model, that relates the change of the Chern-Simons number to the change of baryon number. And so this process, therefore, gives you non-zero baryon number. And so in the Electroweak Theory, if you form textures and you have CP violation, it would give you a non-zero baryon asymmetry. This was pointed out first by Turok and Zatrosny in 1990. as a possible way of generating the baryon asymmetry. More recently, people have studied this in a context of the end of inflation, where the universe is cold and empty, and you can have this transition happening at 0 temperature, and that's what is known as the cold electroweak baryogenesis. And in that case, this process can be important. But if you are at a non-zero temperature in a normal thermal electroweak phase transition, then everything is dominated by the dynamics of the gauge field, and you never really form any textures as such. It's always the gauge field which drives the dynamics, and therefore in the normal thermal electroweak transition this process is not important, but in some other cases.
Can I just ask about the CP violation?
Uh-huh.
So what is the operator that's giving you the CP violation?
I think what they had in mind was the usual phi squared
FF dual.
FF dual. Okay, so the message from here, for the rest of the talk, is that the same thing. We actually have the similar thing happening in the case of vortices, and just like here, we can't just think of Kibble mechanism forming the defect, the texture of vortex, and then the gauge field compensating it. One really has to also take into account the gauge dynamics, and it plays an important role too. In the case of vortices, what happens in detail is a little bit different. So in the broken phase, again, you minimize the energy, and therefore A has to be equal to gradient of the phase, and from that you can immediately see that there can't be any magnetic fields in the Higgs phase, because the magnetic field is the curl of the gauge field, and it has to vanish if the gauge field is equal to a gradient. However, if the field phi is 0, then the phase angle is not well defined, and those points, which is precisely at the vortices, the strings, you can have magnetic field. So the magnetic field is confined into the cores of the strings, and the magnetic flux is just the contour integral of the gauge field around the string, because of this condition, is equal to 1 over E times the change of the phase angle around the string. So winding number times 2 pi over E, it's known as the flux quantum. So a string in gauge theory carries always an integer multiple of this flux quantum. Flux is quantized. Okay, so let's now think of again, the first order phase transition in a gauge theory at a non-zero temperature. Very simple setting. Again, you have these bubbles which nucleate, grow, and collide. And usually, when you have collision of 3 bubbles, I mean, they don't have to collide at exactly the same time, but there is generally a hole left between them. And if the typical radius of a bubble is r, then the area of the hole is proportional to r squared. And now what can happen if you are at a non-zero temperature is that there is some thermal, just because of thermal fluctuation, there is some magnetic flux in going through that hole before the bubbles touch. And one can estimate that in a simple way. It's basically just calculating the energy of a dipole of that size, and you find that the sort of typical flux, the flux of course can be positive or negative, but the typical value, the root mean squared value, is the square root of r It was the radius of the bubble times temperature. Higher the temperature, the more flux you normally have. And now what you had was some flux going through this hole, but everywhere around that hole you are in the Higgs phase where you can't have any magnetic field. So the magnetic field that you had here is trapped. It can't go anywhere. It's a conserved quantity, so it can't decay. So it will. The only thing it can do is when the bubbles eventually grow and fill the whole space, the magnetic flux is squeezed into a string. And if the flux was this, then the winding number of the string would be pi over flux quantum to E times square root of T. So basically what this is saying is that when you have gauge fields at non-zero temperature, when the bubbles collide, they can give you strings which have high winding numbers, assuming that this number is large. And here's a simulation too. Just to clarify that, in a Kibble mechanism, I can quite easily see that you can't produce a string with its binding number higher than 1. It's at most, so it's either plus or minus 1. So if you have binding number 2 or more, then it must have been produced by something else. So now here is a simulation of a first order phase transition. Here you can see a bubble starting to nucleate. So the different colors are again different phase angles. We start in the symmetric phase with some temperature. The white is broken phase, and you can see how the bubble starts to grow, and there are more bubbles nucleating. Eventually they fill the whole space. Then I switch. Now the bubbles are colored, and the symmetric phase is white. The bubbles have now filled almost all the space, and because of the latent heat, they've heated up the holes between them. Gradually, when the universe expands, they cool down, and you're left with just the strings. And here you can see, just as predicted, there's for instance a junction, 2 winding 1 strings merging into winding 2 string. And similarly here. Okay, here's a better picture of the same configuration. So you get, from a first order phase transition, you get these strings with higher winding numbers. In 2 dimensions you can do bigger simulations and you can get higher windings. So for instance, so remember the colors here correspond to the phase angle. So here is a winding number of roughly 10, I think. You go around this point, the phase changes by 10 times 2 pi. And this shows the magnetic fields of the different.
So I didn't now understand this. Geometrically, if you have 3 bubbles colliding, you only get winding number 1.
Yeah.
Is that correct?
Yeah.
And then the other argument was all of the magnetic field goes into strings and you get.
That's right. So if you don't have any magnetic field, if you are only looking at the phase angles, then but you just have 3 different phase angles which you are interpolating.
Okay.
The most you can get is 2 pi.
Yeah.
But if you have gauge fields, you can have in the hole between them you can have arbitrarily high magnetic flux, and that will all get squeezed into the string.
So then the formation of the string doesn't really depend on the orientation of the fields in the bubbles, but only on the flux. Okay.
So this is like, if you compare with the Electroweak case, this is now corresponds to sort of the sphalerons. There's really nothing to do with the dynamics of the Higgs field, but the dynamics of the gauge fields. Okay, a similar thing also happens if you have a continuous second order transition. Again, magnetic flux is conserved, and you can easily see how this is going to work if you think of having initially a uniform magnetic field. We gradually cool the system into the Higgs phase, the broken phase, and if you have a uniform field, that field, because magnetic flux is conserved, it can't go anywhere, so it will still be there after the transition. The only thing it can do is to form a lattice or lattice of strings, a bundle of strings with density, number density just B magnetic field divided by the flux quantum. And that is of course what happens in a superconductor. If you put a superconductor in a uniform magnetic field, cool it in the superconducting phase, you get not because of flux lattice. And if you think of not a uniform field but some thermal initial state, some non-uniform fluctuations, what happens is that when you cool it, you always cool it at a finite rate. And so the shortest wavelengths always have time to decay, but the long wavelengths will survive. And it's still easy to see that you don't know exactly, you have to find out how long the wavelength has to be, you have to do more detailed calculation, but if you think of a magnetic field fluctuation that is a wavelength comparable to the horizon, cosmological horizon size today, it's clear that if you do a quick phase transition, it will be totally indistinguishable from a uniform field. And in fact, in these experiments, of course, they never have a uniform field, they just have a long wavelength field. So a long wavelength field.
On the other hand, the causality requires that correlation length of this magnetic field cannot be larger than Hubble horizon when it is created.
Yes.
So
Well,
how you are?
I'll actually come back to that, but yes, well, yeah, let's say that for the moment. Yes, that's so that doesn't matter because we are not talking about any correlations here. The magnetic field, we're just talking about right. Okay, I'll come to that point. So let's now just imagine that the critical length scale is significantly shorter than the horizon size, which it normally is. But if you think of an experiment in a lab, it really doesn't have anything to do with the size of the cosmological horizon today. And the same is true for any phase transition which takes place in a time which is much shorter than the Hubble time at that time. So the microscopic timescales in cosmology are generally much shorter than the Hubble time. So yeah, so the longest wavelength modes will survive, and just like a uniform field, they will form strings. And the places where the field is pointing this way, you get strings pointing that way, and so on. Okay, be a little bit more precise with that, and basically saying that the correlation function at long distances for the winding number density has to be equal to because the magnetic field is conserved, has to be equal to constant times the magnetic field correlation function before the
And what is the lambda C?
Sorry?
What is this critical lambda here?
Well, so that's a question which I won't really try to answer in this talk. It depends on the dynamics. So it's something you would have to calculate for any particular system separately. But in general, you know that there is some critical length. It can't be infinite, and it can't be zero. So basically, you know that the correlation function, if you know the correlation function of the magnetic field before the transition, the prediction is that the correlation function of the winding number density, the string density after the transition is equal to that at long distances, up to constant.
And the last equation, can you give? The last equation shows you that this field is Gaussianly distributed. Yes.
Yeah. So I'm assuming that. Yeah. So okay. That's no.
Yes, this is just a general form of the Gaussianly distributed function. these projection operators gives you the divergence.
No, I think this only, no, this doesn't assume that it's Gaussian. This only assumes that it's
Divergence free, but it is Gaussian. It is a general form to present only the Gaussian with
I mean,
distributed.
no, it's certainly true that if it's not Gaussian, this doesn't uniquely tell you the distribution. But
the form
this equation
is
is always
transversal.
Yeah.
this is just follows from divergence.
Yeah, it's a gauge invariance.
Yeah.
It's
But yes, in practice, I'm assuming that
because you actually
initially, yes, no, that it is actually important because
You're
the
talking about
the delta function implies it's Gaussian, isn't it?
Yes.
You're,
Yeah.
not the
This-
projector.
I just
Sorry?
know from
Oh, the delta function.
It's
is
the
not-
delta
turbulence
the
stuff,
delta function
yes.
follows from translation invariance.
And also because it
No,
depends
it's
on the
momentum
K,
space.
this power spectrum.
No,
G
for any
depends on
translation-
K. It means the Gaussianity was a delta function. Yes.
So I thought you were talking about the delta ij, ki,
Yes.
kj. That form is just gauge invariance.
Yes, and the divergence free from the projection
Yeah.
operator. And there is a dependence on the module of the K. So as I know, if the field is not Gaussian, you cannot present the two-point correlation in this way.
You would have to have some function of k and q
Yeah.
separately.
Yes.
Is what you're saying.
No, you can't. I mean,
And so this is
this,
your Gaussian in this.
this delta function here follows from translation invariance. It's nothing to do with Gaussian.
Yeah, I guess if you would Fourier transform and do translation invariance, that's what you're saying.
Yeah.
You get delta function. Sure, so.
But I mean, the fact is that there are more correlators. I mean, if it's
Yeah.
Gaussian, that's the only correlator. But if
Yes.
it's not Gaussian, then there are more correlators. But that's not the issue.
Yeah.
It's just that this correlator is.
Translation invariance and gauge invariance.
Yeah.
Yeah.
That's right.
But there could be more correlators. with
Yeah,
more
so if it's
information.
not Gaussian, it doesn't tell the whole story.
Yes, of course.
But this is still, this is general. You can't always write it in this form. Because yeah, the binding number, because it is discrete, it has integer values, it won't be Gaussian, so in that sense it is an important point. Right, so there are two different cases one can consider specifically. Just you can calculate the initial correlation function for the gauge field, either in thermal equilibrium, this is at a 3 level non-zero temperature, you get this, and at 0 temperature it's just a vacuum, and you get k over 2. And and so what's the interesting prediction that you get from this is that so these are calculated for the magnetic field in equilibrium before the transition, but the strings will have the same correlation function after the transition, and especially at long distances, this will give 1 over distance cubed, this will give 1 over distance fourth power. So you have a long range correlation in your string network coming from the correlations that were present in the gauge field before the transition. This is something you couldn't get from the Kibble mechanism because it is precisely what is based on is the assumption that nothing is correlated at distances longer than psi. So the prediction here is that you get long range, in principle infinite range correlations, and one can also try to search for those in the simulations for your readers. So what I want to do is to do simulations with different couplings, because the amplitude of this correlator goes like E squared. So we should find a different correlation for these different values of E. Do simulations, get these string networks, and indication is whether they have different correlations at long distances. And this is obviously a question that you can't answer by just looking at them. They look identical, but you can just take the data and calculate the correlation function from the data. And so this is for 0.1, this is for 0.5, and the prediction was that it should go like E squared, so you would expect more correlation for at low k, at long distances for higher E, and that's what you get here. And in fact, the predictions were not just qualitative, they were quantitative, and the predictions from this flux trapping are the solid lines here. You can see that asymptotically it really seems to be approaching them. The dashed line is the prediction from the flux trapping plus a fit to the one parameter fit to the form that you could expect to get from the Kibble mechanism. And you can see that it fits the data very well. So the conclusion here is that it seems that you can actually think of there being two sort of different additive mechanisms. There's flux trapping and there's the Kibble mechanism. You can just, in a sense, add together, and the correlator is the sum of the two contributions.
Sorry, so you're saying the dashed line is the
So this is what you get
from the Kibble mechanism?
Yeah, dashed line is, so the solid line is just this. At low k this just becomes approaches a constant. And then I add, Kibble mechanism gives essentially number times k squared. And so I add that kind of a term and do a fit to get the coefficient. And
it's a quadratic fit.
It's a quadratic fit, yeah, but it's motivated by Kibble. So it seems that it actually works nicely. And what I think is even more interesting is you can do this also at zero temperatures. It's just that this is a classical simulation, but I put in the quantum fluctuations. Classical fluctuations have the same two-point function, statistical two-point function as the quantum fluctuations. And what we find is, again, the prediction from flux trapping is the solid line. The data approach it quite nicely. And again, you can add a k squared coming from the Kibble, and it fits nicely. Now, so what? Okay, and yeah, I'll just show you a movie of what happens. So this is all at long distances where you really see a different behavior. So for Kibble, you just get k squared. So this is qualitatively different from what Kibble mechanism would predict. And this is the dominant mechanism at long distances. As I showed you a movie of what happens at short distances because it's just quite cute. Because you remember what the mechanism was, that you have this long wavelength magnetic field which freezes out and turns into vortices. So you would expect to have regions where you have vortices pointing one way, regions where it's pointing the other way. And that's exactly what you get. You have these kind of clusters of vortices of positive sign, vortices of negative sign. And so that's just quite cute. And one can estimate what the size of them is and how many vortices you have there. And for the Kibble, you don't get any clusters. And people have seen this also in three-dimensional simulations. Right, so yeah, I won't really go into too much detail about what this might mean. The short distance effects are not important for cosmology because they will be washed out very quickly. We are talking about dynamics that is distance is much shorter than the horizon size. Now these very thick strings that you get in first order phase transitions can be important because they have these junctions generally between them, and they prevent the strings from moving freely, and therefore it's not clear and it's not known if that kind of a network will scale in the same way as a network of single winding strings which is known to scale. And so therefore the predictions could actually change, and this is something that needs to be studied. The long-range correlations, on the other hand, are more interesting because, especially, so now I come to this question about whether they can have correlations at superhorizon scales. Now, in old-fashioned Big Bang, pre-inflation, pre-Guth Big Bang theory, you wouldn't have an answer to that question. There was no way of saying what happens on superhorizon scale. So therefore, you had to put in the initial conditions by hand. However, with inflation, if there was a period of inflation, we know that those length scales were initially inside the horizon and were in the vacuum state. And so therefore with inflation, we would be in the situation where we have the vacuum spectrum at very long distances. Distances which were superhorizon at the time when the strings formed but have now entered the horizon. And the interesting thing here is that it actually makes a prediction for, though that kind of distance, it says there should be a correlation, 1 over r to the 4th correlation, over distances that appear to be causally disconnected in a normal Big Bang scenario. Okay, right, so it's interesting because it seems that we get something out of nothing. The initial state was just vacuum, but you still get this infinite range correlation. Now, as I said, all of these actually, because I haven't been very specific about the model, everything I've said should also apply to superconductors. People have been trying to do experiments to test these, and here is just a nice picture from one experiment where you can sort of see the clusters appearing as predicted. However, it's not entirely clear what was happening in that simulation, sorry, in that experiment. So yeah, I wouldn't necessarily say that it's the same. Those are the same clusters as in this picture. But they could also, in principle, measure the correlation at very long distances, as long distances as they can go to in the experiment, and therefore test those predictions. Right. So that was all I was going to say. Basically, what the message here was that, well, first of all, that there are similarities between defect formation and electroweak baryogenesis, but many things have parallels. This is again producing some relics from a thermal phase transition, but in this case things are a lot simpler. It's easier to do estimating and calculations of how things go. And what the results indicate is that just like in the electroweak case, they, especially at long distances, it's the gauge field dynamics that is more important, and it gives rise to either thick strings in first order phase transitions or long range correlations in second order phase transitions. And in principle, at least, people should be able to test these in superconductor experiments. So that gives a way of sort of doing cosmology, in a sense, in a laboratory. I hope people can really do. Okay, thanks.
Yeah, thank you.